So now let's learn a little about the sandwich or squeeze theorem. Two names mean the same thing. If we can't find a limit directly, we may be able to find it indirectly with the sandwich theorem. The theorem refers to a function f whose values are sandwiched between the values of two other functions g and f. So one of the requirements is that the function has to be sandwiched in between two other functions. If g and h have the same limit as x approaches c, then f has that limit too. It's true if and only if f is sandwiched in between g and h on a closed interval containing c. So if we have a function, it's sandwiched in between two other functions on some closed interval about the value that we're taking a limit as x is approaching. And the two functions this function is sandwiched in between have the same limit at some point c, then our function has to have that limit as well. Right? So it has some requirements, but if the requirements are met, we can find our limit indirectly using two other functions. So let's take a look at what it looks like visually. Suppose the function f of x is in between two other functions, g of x and h of x. Not only that, but as the limit as x approaches c for g of x and h of x is equal. As a result, the limit of f of x as x approaches c must be the same as for g of x and h of x. If f is in between the other two functions and at some point the two functions are equal, that means that all three functions have to be equal because our function here is sandwiched in between. Notice there is an open hole there, right? And so we'll talk about that in a second. But that point does not c does not have to be defined for any of the functions. Right? The limit just has to exist as x approaches c. So sandwich or squeeze theorem. If h of x is less than or equal to f of x is less than or equal to g of x for all x in an open interval containing c except possibly at c itself, which means that f of c, g of c, and h of c do not necessarily need to be defined. And the limit of h of x as x approaches c and the limit of g of x as x approaches c is equal to the same thing, and f of x is in between or equal to these two functions, then the limit of f of x as x approaches c exists and is equal to L. Right? So let's take a look at this in action. All right, so here's our first one. All right, so we have the limit, we're trying to find the limit of f of x as x approaches 1. And we don't even know what f of x is. But we know what g of x is and what h of x is. So g of x is x to the fourth minus 2x squared. And h of x is negative x squared plus 2x minus 2. It's given that x to the fourth minus 2x squared is less than or equal to f of x, which is less than or equal to x squared, negative x squared plus 2x minus 2. So let's find the limit using the squeeze theorem with a justification. When we use the squeeze theorem, remember you got to justify why you were able to use it. All right, so let's find the limit of g of x as x approaches 1. All right, and so to do that, it's a polynomial function. We can just plug in. All right, so we're going to evaluate. So we would have 1 to the fourth. Oops, that looks like 14. So notice here, I didn't write the whole function. I wrote g of x. That's fine if your function has been identified as g of x or h of x or etc. All right, so the limit of g of x as x approaches 1 is going to be 1 to the fourth minus 2 times 1 squared. All right, so let's simplify that. 1 to the fourth, that's just 1. And that's just going to be minus 2, which is negative 1. All right, so the limit of g of x as x approaches 1 is negative 1. Let's find the limit of h of x as x approaches 1. So that's going to be negative 1 squared plus 2 times 1 minus 2. So that's going to be a negative 1 plus 2 minus 2, which is a negative 1. Well, now we can see that the limit of g of x and the limit of h of x is equal to one another. Right. So now let's justify our use of the sandwich theorem. Since g of x is less than or equal to f of x, which is less than or equal to h of x, and the limit of g of x as x approaches 1 is equal to the limit of h of x as x approaches 1 the limit of f of x as x approaches 1 must equal negative 1, 2, using, and you can say sandwich or squeeze theorem. Let's just call it sandwich, using the sandwich theorem. All right, so you have to make sure you've met your requirements, and you need to state that you've met your requirements. We've got the function is in between g of x and h of x, and the limit of those two functions that's in between are equal to one another as x approaches 1. We know that a limit of f of x has to also, as x approaches 1, has to also be equal to negative 1, using the sandwich theorem. All right, so here we've shown that we've met our requirements, we found our limits, we showed we met our requirements, and then we justified it using the sandwich theorem. So make sure when you're using theorems, you show that you've met the requirements for that particular theorem. That's very important on the AP test and in college classes. You have to show that you meet the requirements. So I have to state that f of x is between g of x and h of x. I have to state that the limits are equal. Otherwise, I haven't properly justified why I can use the sandwich theorem and why I was able to find the limit for f of x as x approaches 1. Okay? But actually, I think the sandwich theorem is pretty easy to work with once you get the hang of it. All right, so applying the squeeze theorem, sandwich theorem, whichever you prefer calling it. Suppose you were told to evaluate the limit below. Calculating this limit on its own is very difficult. The function, however, is squeezed in between two functions with the same limit, and this limit is easy to find. And how do we know that our function here is squeezed in between two other limits whose limit is easy to find? We're not even told who these functions are. Well, it has to do with the nature of sine and cosine. In this case, we're working with cosine, but later on we'll see sine. So remember, the cosine of any angle must be between negative 1 and 1. So the most cosine of an angle could be is 1, and the smallest the cosine of an angle can be is negative 1. Thus, when you multiply any number by cosine, its magnitude becomes smaller, right? Because we're multiplying by something that is less than 1 or equal to 1. And if it's equal to 1, it doesn't change, right? So x times cosine blop, or let's go over here. Since cosine blop has to be less than or equal to 1, and cosine blop has to be greater than or equal to negative 1, x times cosine blop has to be less than or equal to 1x, and x times cosine blop has to be greater than or equal to negative x, right? Because the most my cosine could possibly be is 1, and the least it could be is negative 1. Therefore, this part here, the cosine part, cosine of 1 over x, that is constantly sandwiched in between 1 and -1, right? We know that cosine whatever, it doesn't matter what I'm taking the cosine of. You can tell me cosine of elephant, right? No matter what, it's got to be between 1 and -1 and 1, right? It's got to be greater than -1 and less than 1. So if we multiply, we have something multiplied by cosine, right? It has to be less than, it has to be greater than or equal to that same thing, the negative of that same thing, or, excuse me, greater than or equal to the negative of that same thing that we're multiplying by. So here, all of this, right, has to be greater than or equal to -x, right? It's only going to be equal to -x when my cosine blob here is equal to -1. Let's put it over here. And it has to be less than or equal to x. It has the absolute value bars around it just to make sure it's staying positive because it's a variable, right? But when you work with it, you can drop those absolute value bars very quickly. But we just want to, whatever x is, we want to show that it's greater than the absolute value of the negative absolute value of it and less than the positive absolute value of it, right? And so the sandwich theorem becomes really important for sine and cosine because of this property that it's always sandwiched in between -1 and 1. So let's see how this one works in action. All right, so let's look at the limits of -x and the absolute value of -x. I should say the negative absolute value of x and the absolute value of x as x approaches 0. So here, we could take the limit for x times cosine 1 over x for anything but 0. 0 is a problem, right? 0 is definitely a problem. We'll have an indeterminate limit. Right? So you can plug in 0 for x, right? Because x times cosine 1 over x is in between the two functions, is in between -x and positive x. And both of these functions have a limit of 0. X cosine 1 over x must have a limit of 0 as well as x goes to 0. Let's take a look at this visually as well as see this all written out. All right, so since the limit of negative absolute value of x is 0, right, I can plug in 0, no problem. The absolute value of 0 is 0. And the limit of the absolute value of x as x approaches 0 is 0. And, right, so we've shown that the limits of these two functions are the same. And x times cosine 1 over x is greater than or equal to negative absolute value of x and less than or equal to the absolute value of x. The limit of x cosine 1 over x as x approaches 0 is equal to 0, 2. And here it is visually. Right? So it's a little hard to see, especially the lines here. So this function right here, this is y equals negative x. We know that function. And this function here is y equals positive x. Now, look at our cosine function in between here. It bops around a bunch, right? But notice that it is always staying in between those two functions. Maybe I should have made this one a different color. Well, you'll have to deal with both being red. So it's in between the y equals negative x and y equals x for that entire interval there. And notice, graphically we can see all three of those functions are approaching 0. Now, y equals negative x is defined for 0, and y equals x is defined for 0, but x times cosine 1 over x is not defined for 0. I can't plug in 0 there. There's a hole, but it doesn't matter that there's a hole because a limit is defined there. And we were able to show this using the sandwich theorem. So here we showed it, we did it algebraically using the sandwich theorem, and we showed it graphically as well. Let's do some more examples, and we're going to do these just graphically. once you get the hang of this one, seeing that visually, I think the rest of these become a little easier. All right, suppose there are three functions, f of x, which is less than or equal to g of x, which is less than or equal to h of x, when x is near 2. Further, suppose that f of x is equal to negative 1/3 x cubed plus x squared minus 7/3. And h of x is equal to cosine pi halves times x. Determine the limit of g of x as x approaches 2. So g of x, we've met the first requirement. G of x is in between the two functions. If the limit of f of x as x approaches 2 is equal to the limit of h of x as x approaches 2, then the limit of g of x as x approaches 2 is the same. It's not a bad idea if you have this as a problem on a AP test or a Misspershagen test to write something like this down, because you're showing that if this is true, then you're going to be able to use the sandwich property. Then with your work you can show, was it true or was it not true? And then justify your answer. So let's continue on here by finding our limits. All right, so we need to find the limit of f of x as x approaches 2. All right, so now I can just plug in, right, and I don't have to write the whole function since I've defined what f of x is. All right, so this would be negative 1/3 2 cubed. And of course it's polynomial. We can always use substitution with a polynomial. 2 squared minus 7/3. All right, so that's going to be, so 2 cubed is 8. So that's going to be negative 8/3. And then 2 squared, of course, is 4. Now, since I've got fractions with denominators of 3, let's change the 4 to 12/3, right? 4 is the same as 12/3, and then minus 7/3. All right, so that's going to give us 4/3 minus 7/3. That's a negative 1. All right, now let's find the limit of h of x. So notice, by the way, it doesn't matter whether it's which letters you use for which functions, so long as it's been stated that the function that we're trying to find the limit of using the sandwich theorem is in between the other two. Sandwiched in between. All right, so we have the limit of h of x. All right, so now I'm just going to plug in 2. So I have cosine pi halves times negative 2. I'm going to write the negative 2 in front. Oh, excuse me, it's cosine pi halves x. Sorry. That's not 2 times. I misread it. I looked way too quickly. It's the cosine of pi halves times 2. Well, I'm feeling a lot better about that because I didn't know what I was going to do with just a 2 in front, because cosine pi halves is 0. However, cosine of pi halves times 2, all in the parentheses, these 2's would cancel. That's the same as cosine pi, which is negative 1. So now we have the same limit. All right? So now we can justify using the sandwich theorem. So since, actually let me switch colors. I like to switch colors. I think it makes it easier to read, where I do one thing and go on to the next. All right, so since f of x is less than g of x, we lost our x, is less than or equal to h of x for all x near 2, and the limit of f of x as x approaches 2 equals the limit of h of x as x approaches 2. And that limit is equal to negative 1. The limit of f of x as x approaches 2 equals -1, 2, using, and whichever you want to call it, squeeze or sandwich. Using the, I have a tendency to like to use the word sandwich, the sandwich theorem. You got a sandwich, the other two functions are the bread, and that third function is the stuff in between. All right, so the squeeze or sandwich theorem can help us evaluate limits. I should write that underneath here. Squeeze or sandwich. You use the word you like. All right, maybe I'll switch back and forth. All right, so let's take a look at another example. Oops, sorry, I have one little mistake here. I just got it. I wrote the wrong function. In the last problem, it was f of x. That was the one in between. This time, it's g of x. I had to make sure I write the right thing. All right, you be careful on that too. G of x is the one that's in between and the one we're finding the limit of. All right, let's look at another example. All right, suppose there, okay, this is a different one. I thought I had the same one again. All right, suppose there is a function g of x such that f of x is less than or equal to g of x is less than or equal to h of x when x is near -1. Further, suppose that f of x is equal to -1/4 x squared minus 1/2 x, and h of x is equal to 1/3 x squared plus 2/3 x plus 2/3. Determine the limit of g of x as x approaches -1. Right, so let's find the limit of f of x as x approaches -1. Right, so that's going to be -1/4 -1 squared minus 1/2 -1, which would be, so that's that -1 is going to be positive, so that's going to be -1/4. That's going to be a positive 1/2, so positive 2/4, which is equal to 1/4. And we have the limit of h of x as x approaches -1 is equal to 1/3 times -1 squared plus 2/3 times -1 plus 2/3. All right, so that's going to give us 1/3 plus, that's going to be a -2/3, so I may as well just write minus, plus 2/3. Well, that's equal to 1/3. So, because, let me switch colors again, because the requirements of the sandwich or squeeze theorem have not been met, in this case, the limit of f of x as x approaches -1 does not equal the limit of h of x as x approaches -1. The limit of g of x as x approaches -1 cannot be determined. It is not enough to just be between two other functions. Those two other functions have to be equal at some point. And at that point, then you can find the limit of the function that's sandwiched in between. So here, we did not meet the requirements. We missed out on, we met the requirement that g of x is sandwiched in between. We did not meet the requirement that the limit of f of x equals, as x approaches -1, equals the limit of h of x as x approaches -1. So here, we cannot find the limit of g of x. So you have to meet the requirements. Okay? So whether it does or doesn't, you need to justify why you can or cannot use the sandwich squeeze theorem. I think this is my last example. No, it's my second to last example. All right, so we want to find the limit as x approaches 0 of x squared e all raised to the sine 1 over x. So you can see you cannot plug in 0, right? If then I have 1 over 0. You can't take the sine of 1 over 0. That's not a number. It's undefined, right? So how do we know? Because we're not told here. And the last problem, see, here we were told that g of x was in between f of x and h of x. We're not told that g of x is in between f of x and h of x. However, if we think about it, we can determine that it is. They are that as soon as we figure out what f of x and g of x are, we can figure out, right, that g of x is going to be in between f of x and h of x. We just have to choose the right functions. Right? So sometimes you're not given the function that you're sandwiched in between. However, let's think about sine. Sine, like cosine of any angle, has to be between -1 and 1. Right? So we know the middle function, our g of x, is going to be this whole thing, right? That's what we're trying to find the limit of. X squared e to the sine 1 over x. I need to write that smaller. There is absolutely no room for the other functions there. Let's write small. It's an exponent. I have to write really small. Small. There we go. That thing is supposed to be an x. All right? So now we have to think about what are the other functions going to be. All right? So now, what if sine 1 over x is as small as it can, actually let's go as big because h of x is the biggest one, is as big as it could be, right? If it's as big as it could be, it's 1, right? So now let's think, if sine blah there is 1, what do we have? We have x squared times e. Right? Which have it raised to the first power. Right? That's the most that sine could ever be. What's the least that sine could ever be? What if sine 1 over x is equal to -1? Now it's the least it could ever be. Right? So now, what are we raising e to? Well, that would be x squared times e to the -1, which is x times, so I could write times 1 over e or put e in the denominator. Right? So now e goes to the denominator. So that's the smallest that x squared, oops, we lost the square there. So the largest x squared times, the largest value x squared times e to the sine 1 over x could be is the same as x squared times e. The smallest value that x squared times e to the sine 1 over x could be is x squared divided by e. So we use the sandwich theorem with sine and cosine because it's limited, right? It has to be greater than equal to -1 or less than or equal to 1. All right, so that's why we can use the sandwich theorem with sine. All right, so now let's see if we meet the requirements here. All right, so we're looking at as x approaches 0. So let's find our limits. Oops. So the limit as x approaches 0 of h of x, right, that's going to be 0 squared times e. Well, that's 0. The limit of f of x as x approaches 0, that would be 0 squared divided by e. That's still 0, right? If you multiply 0 times e, or zeros in the numerator of a fraction, that's still going to be 0. So notice the limit of f of x as x approaches 0 is equal to the limit of h of x as x approaches 0. And I think I left this up here. And actually, let's just go like that, and it'll move a whole lot faster. There we go. All right, so since the limit of f of x as x approaches 0 equals the limit of h of x as x approaches 0, and f of x is greater than or is less than or equal to g of x is less than or equal to h of x, then using the squeeze theorem, the limit of g of x as x approaches 0 is equal to 0. So I made it nice and compact in this one. Right? So here we use the sandwich theorem. Right? We're going to use the sandwich theorem one more time. So sometimes you're given the function, and sometimes you got to use your brain and think about what two functions our function is sandwiched in between. With sine and cosine, it's going to be easy. Right? You're just going to multiply. You're just going to make sine be 1, or you're going to make sine be negative 1. Here's our last one. All right, now we got cosine. All right, so in this case, f of x is going to be less than or equal to g of x. It's got to be less than or equal to h of x. Our g of x, the thing we cannot find the limit of, is the x cubed cosine 1 over the cube root of x. Cannot find that limit. X cubed goes to 0, and now you've got 0 in the denominator. You can't take cosine of something that's undefined. All right? And it does not exist. All right? It's just that in the format it's written in, we cannot find the limit directly by substitution. Substitution does not always work. All right, so f of x is the small one. That means that if cosine, and I'm just going to put blop, because I don't feel like writing all of that, and I don't have that much space, is equal to negative 1, right? Because cosine blop here has to be equal to, less than or equal to, I'm writing cosine blop here, negative 1, and it has to be, cosine blop here has to be greater than or equal to negative 1, and less than or equal to 1. If I read my inequality signs backwards one more time. All right, so if it's the negative 1, if cosine blop is negative 1, then we just have negative x cubed, right? This whole expression there could be at its smallest, and its smallest is at negative x cubed, because cosine whatever's smallest value is negative 1. Cosine's largest value is positive 1, and that would make it x cubed. Right? We know that x cubed times cosine blop there has to be between those two functions, right? Because cosine has to be between negative 1 and 1. So when we multiply this cosine blop here by x cubed, it's always going to be, the most it could be is x cubed, right? And the least it could be is negative x cubed. And if cosine blop is anything but 1 and negative 1, it's something that's smaller than 1 and negative 1, right? Because cosine blop is sandwiched in between 1 and negative 1. And if you multiply something by something that's less than 1, right, whose absolute value is less than 1, it gets smaller, right? So we know g of x here has to be sandwiched in between h of x and f of x. All right, so let's find our limits. Oh, this podcast is a little longer than I thought it would be. I'm trying to give you lots of explanations so to make sure you understand a very important theorem. So the limit as x goes to 0 of h of x, well, that's 0 cubed, and that's 0. The limit of f of x as x goes to 0, well, that's negative 0 cubed, and that's still 0. So, and we switch colors. I'm doing a good job switching colors here. So since the limit of f of x as x approaches 0 equals the limit of h of x as x approaches 0. And g of x is greater than or equal to f of x, but less than or equal to h of x, then the limit of g of x as x approaches, actually let's put the sandwich theorem here first. Then using the sandwich theorem, or squeeze, the limit of g of x as x approaches 0 is equal to 0 as well. And by the way, that function is undefined. The x cubed times cosine blob there is undefined when x is equal to 0. We can't plug it in, but from the right side and the left side, it's going to be approaching the same value, and that value is 0. All right, so that's the squeeze or sandwich theorem. Boy, I talked a lot. And now I have some problems for you to do. All right, thanks for watching. Bye for now.